Hello, good morning. I hope you had a good Veterans Day holiday yesterday. So today we will continue to discuss static equilibrium. So as we mentioned this on Wednesday, for an object to be in equilibrium, which means that it's not moving and it's not rotating, right? So you want the linear acceleration to be 0, and you also want the angular acceleration to be 0. For linear acceleration A to be 0, according to Newton's second law, F equals ma, you want the total force to be 0. For the alpha angular acceleration to be 0, you use torque is equal to I alpha. You need the total torque to be 0. So let's take a look at this question. This particular setup is similar to one of the bridge questions we did in the pre-lectures. So let's answer this one first, and we can figure out how to write out the torque equation. If we are looking at the equilibrium of the total torque about the hinge, so it's relative to this point, okay? Relative to that point, there is no rotation. So relative to that point, you want to add up all the torque and make them equal to 0. So this is what we're trying to write. And since we are rotating relative to the hinge, you can see we did not draw a force on the hinge because that force is not going to give you any torque, right? Because you're looking at the rotation relative to that point. There's no level arm for that force, which means we only need to add up 2 torques. One is from gravity of this beam. One is from the tension. So this beam is being pulled up by the rope right here. When we draw gravity, we always draw gravity to be acting on the center of the mass of the object. So usually without particularly saying, we always think this is a uniform. If it doesn't say, it means it is a uniform distribution. So the center of the mass of a long beam would be at the center. So that's where you would put the gravity for that object. So right in the middle, okay? And then the tension is pulled at an angle, okay? So which one of these correctly represent the sum of all the torque is equal to 0? So I'm gonna go ahead and let you vote. All right, so let's have 10 more minutes to wrap up. 10 more seconds on this question. Okay, all right, let me go ahead and close. All right. Okay, very good. So given the choice, a limited number of choices is usually not too difficult to write down the torque equation, right? For example, we see that, well, the torque from gravity has a 90 degrees with respect to the level arm. So the one with mg times L over 2 should not have a sine theta, right? So it's easy to narrow it down to one of the choices, but the tension does have an angle with respect to the radius. So given the choice is not hard and A is correct, very good. But let's look at, well, if we have to write this down ourselves, how do we do it more systematically? So here we have two forces. We need to sum up the torque from these two forces. And let's look at the gravity first. So gravity, the torque by gravity is force times the level arm, which is this distance L over 2. The angle between them is 90 degrees, so it's really just mg times L over 2. And then let's add the plus or minus sign. So if we say counterclockwise is positive, gravity is trying to rotate its beam about the hinge. So gravity trying to pull it down. So it's trying to rotate it in the clockwise direction, right? So that torque is negative. So we're going to put a negative sign for the torque by gravity. That's the first one. The second one is the torque by tension. All right, so we know that has to be positive because by you can see by pulling the rod, this direction is trying to do a counterclockwise rotation. So that's positive. So how do we write down the magnitude? We know that torque is R cross F, which is R times F times the angle between R and F. Okay, so here R is, let me label it from the rotation where the pivot point where you're going to rotate to where the force is being applied. So this is my R, you see, this is my R, this is the F. Actually, the angle between them, because my R is extending out this way, the angle between them is actually this angle. But just so that this angle is really just 190 minus theta, and it's equal to sine theta. So sine of this angle is equal to the sine of the smaller angle that was given in the problem. So the torque from the tension is T times the magnitude of R. You can see that's the entire length of the rod is T times L times sine of theta. So these two add up to be 0. So A is correct. Okay. Another way to look at the cross product, I'm not sure if that helps you or if that is easier, is you can always interpret the sine theta, the sine angle, together either with F or together with R. If you combine this with R, you're looking at what is the level arm. So what is the distance that is perpendicular to the force? Because only that distance matters, right? So in this case, your force is along the rope. Only this distance is the distance that matters. That's your level arm. So if you look at that distance is L sine theta. Using SOHCAHTOA, you know this is L sine theta, and you can use T times this level arm directly.
Professor.
Yeah.
So this might sound really stupid, but if we get tripped up a lot, I get more tripped up doing it with angles than I do with the cross product matrix process. Is it okay if I do it with we do with a matrix process on the test?
You mean like here? You mean this method?
If you're trying to draw something, I don't see it. I'm sorry.
Oh,
is it just like the IJK on top?
Okay, so what is the method that you were trying to use?
So what I do is if it's a 3D vector, like on our homeworks, I'll just put like an ijk on the top, and then the bottom row will be the r vector,
Okay.
and then the f vector to be the third row, and then I'll make it a matrix and then do it that way.
Okay, sure, certainly. So you're
It's
saying,
just I get less tripped up with angles. I get less tripped up that way on the homework than with angles. So I just wanted to know if it was okay to do it if it was easier.
of course, in this case, I'm not sure if that's easier because if you do the matrix, your R is you represent it using LX hat or I hat.
Yeah. Yeah, no, and this question would probably be harder. But some of the homeworks have been like 3D.
Yeah,
Yeah.
sure.
but-
Yeah, sure, absolutely. If you do that, then T will be you need to get into I hat. You need T cosine theta negative I hat and the T sine theta J hat. Then you have to break it down and then do your matrix cross product between
Yeah.
R and T. That's
Okay.
absolutely okay. I just don't know if that's easier. But that if anyway, whatever works for you, you individual, pick a method that you are less likely to make a mistake. You
Okay.
can do
And for
cross
extra, I
product.
mean, for terms of like on the test, partial credit, if as long as we do the method right, and
Mhm.
it's like then we'd still get the partial credit, right? Even if we didn't do it
Yeah,
with
absolutely.
okay.
I'm not gonna say which method you have to use as long as you get the correct torque. Yeah.
Okay, thank you.
Okay, so that's how we try to interpret this cross product. Now, if you do group the angle and the force together, saying, well, I just want to look at what the component of the force that is perpendicular to the beam. In that case, you will do, well, only this force is providing a torque that is a T sine theta component. So you get a T sine theta times L no matter what. So depend on how you want to group your angle, okay? But just as long as you pick a method that you like and stick with it.
Professor.
Sorry,
Yeah,
go
go ahead. Jacob and then Berenice.
Bernice, you can go first.
Okay, go ahead.
Oh, thank you. I just wanted to ask, I got a little tripped up with the angles too, and then the cross product. So, when we're looking at gravity,
Mhm.
the distance, we're just looking at the distance from the hinge, right?
Yeah,
Because I was confused because the way I kind of did it, I included the whole diameter. So I want to know like what's since we're looking at torque, I was confused about why we only included only half of that.
oh, because you apply this gravity only halfway from the hinge.
Right.
Not applying the gravity all the way at the end, right? Like if you're pushing a door, this force is sort of you're pushing it in the middle. You're not pushing it at the doorknob. That's why you can see the distance is only half, because we say gravity acts from the center of the mass of the beam, and the center of the mass is right in the middle.
Okay. And then then for the tension,
Mhm.
that's where we include the whole diameter, correct?
Yes, because tension is applied at the end, right? Not in the middle.
Oh, okay, I see.
Yeah, very good question.
Thank you.
Okay, and then another question from Jacob.
Yeah, sorry, I got a little confused with the sine omega and the sine theta. So
Mhm.
omega is the outside angle outside of t, right? As you drew. So in the answer to the problem, it's TL sine omega or TL sine theta.
It should be using the angle that you were given. So I was showing that angle because this is actually this is R, this is T. Okay, so you can see these two are making an angle not here because this is a vector pointing this way. I can move my R parallelly a little bit to the right, showing my R this way. So this is the angle that they made. And this angle is 180 minus the angle that was given, minus theta. But but this is equal to sine theta, right? So your final result should be LF sine theta.
So sine theta and sine omega are equal.
Yes, it is equal because phi is 180 minus theta. So if it is 30 degrees, this is 150 degrees. Sine of 150 is the same as sine of 30 degrees.
Oh, shoot. Yeah. Okay. I see it.
Yeah, it's because of that.
Okay. Thank you.
Okay, so this is using the cross product view. This is one method. Like I said, you can never mind that method. Just look at, okay, what is the level arm I need? And you can get this sine theta to come out anyway. So, or you can look at the perpendicular force component. You can get that sine theta to come out as well. Okay, all right. So if we know how to set up the torque equation, then we can answer this bridge question because it's exactly the same. We are given two different cases, and they tell us the angle is the same, right? With the plank, but just the length of the beam that we're trying to support is different. One is L, one is L/2. So in which case the tension is the biggest. So you can see that, okay, if I were to draw the force tension in one, and this is my gravity, again, gravity acted from the middle point, the mg. Now do the same thing. I have tension in two, and again, I have gravity mg. So if I try to solve for tension, I can start with the force equation, or I can start with the torque equation. So in this case, starting with the torque equation actually is quicker and easier because the torque equation gives us directly tension times L times sine of theta minus mg times L/2 is equal to 0. This is from our previous question, okay? So that is exactly the same as case 1. Our length is L and halfway is L/2 for gravity. So from here, you can see if I cancel my L, I got tension in case 1 is mg over 2 divided by sine theta. Okay, so that's in case 1. Then you realize you can do the case 2, but at this point you realize, oh, the L, the entire length of my plank didn't even enter into my equation. You can see my tension is depend on the gravity, and it also depends on the angle. It does not tell you how long it is. It doesn't matter. So in this case, you know tension 2 will be exactly the same. You could set it up. If you did want to set it up again, just to make sure, you would say tension in 2 times the entire length. Now the entire length is L/2, right? Okay, L/2 times sine theta minus mg times the level arm for gravity is half of the L is L/4, and you cancel the L, you get the exact same result, right? 2 of sine theta. So you can see that the tension is the same in both cases. So C is correct. Okay. Any questions so far about this particular shape and how we set up our torque equation for that shape? Are we all good? Okay, now let's move on to look at a different question. Here we have a door that is rotating relative to the hinge point as indicated here. You have two forces acting on it. A big force acting much closer to the hinge, a smaller force acting further away on the other side of the door. And we know that the door does not move, so we know all the torque and forces has to balance for it to be in static equilibrium. So we're trying to figure out what is a force by the hinge. There must be some force on the door from the hinge. In which direction is it pointing? Or is it 0? So this is what we're trying to figure out. You know that you need to balance all the forces and you need to balance all the torque. You can start with one of them, see if that gives you the answer. For this one, let's have a discussion for a minute or two in our breakout rooms, and then we can come back to vote. And I believe I'm joining room group 5 or 6, or maybe joining group 6 today. I think I went to group 5 last time. All right, take a screenshot before you leave and a minute or two for discussion. Hey, hi everyone. So what do you think about this question? Let's think about it together. When we have forces in many different directions, it's always easier to break it down into components, right? So the big one, the big force is already in the perpendicular direction. The small force acting at an angle. So let's say if we break it down into a component pointing downward and a component pointing to the left. Okay, so I'm gonna get rid of my original small force and see, okay, now I have one force to the left, one force down. So what do you think? In order to balance all that forces, what kind of force do you need from the hinge? All right, so Dylan said, I'm thinking it's D. So you need a force in the diagonal downward direction. Very good. So if you need it, that force will certainly give you a component pointing to the right. So one is the right, one is to the left. That's balanced, good. And you also need another downward force, right? So, so this one is downward, this one is upward, but this one is bigger, this one is smaller, right? So you need another downward force so that the two forces pointing down can balance the one force pointing up so that our force equation can be satisfied. Yes, very good. It turned out we can just use the force equation and we can figure out the direction about the force from the hinge. We don't even need to go to the torque equation. Very good. I will see you shortly when we return. All right, let's wait for 10 more seconds to wrap up. All right, any last minute vote? Okay, I'm gonna go ahead and poll. We'll take a look. All right, it looks like one of the answers, choice D, gathered more votes than the other one, but we do have quite a spread across all these different answer choices. So we want door to be in static equilibrium, we need to balance out the forces. So we have one force that's pointing upward directly, and we have another one pointing diagonally down. So let me just go ahead and break this force into its components because that's easier if everything is either on the X or the Y direction, right? So this one is equivalent of having a force to the left and another force downward. So after I have already considered this force, I break it down, I'm gonna cross it out. So right now what I have is one force to the left, one force down, one force up. To balance that, what kind of force do I need? What kind of force do I need in the horizontal direction?
Force pointing to the right.
Force pointing to the right, very good. So that has to be coming from the hinge to balance the force to the left. And do I need a vertical force at the hinge? Since you already have one downward, do you think this one can balance the upward force?
Yeah, because it's a lot closer in. So the torque's probably going to balance out, vertically speaking.
Okay, yes, but we're not talking about a torque. Torque needs to be balanced. Force has to be balanced as well. Now I'm just talking about the force.
Oh, so then, yeah. Oh, that's a good point.
Yes.
Probably not then.
Okay, then you do need another little downward force because this one is smaller than the upward force, right? So it has to be downward from the hinge. Okay, so the overall force at the hinge is a diagonal direction to the right, downward to the right. Okay, so D is correct in this direction. To look at the torque though, okay, to look at the torque, there are many choices. If you want to put the point of rotation, like, okay, relative to which point you are rotating, a very natural place is to put it at the hinge. If you put it at the hinge, the force from the hinge doesn't matter. I think that's probably why some people voted for 0 because they were thinking about the torque. Okay, now if you put it at the hinge, I agree, the force from the hinge does not give you any torque. The torque needs to be balanced by the bigger and the smaller force. So the smaller, you can see, is trying to rotate clockwise, the big force is trying to rotate it counterclockwise. And the smaller force also has a longer level arm. The bigger force has a shorter level arm, making it possible to also balance the torque. But that's not the only way to look at this. You could have picked, let's say, the center point, and you wanted to look at the rotation relative to that point. And they're supposed to be balanced as well. Just that if you have shifted your rotation axis, then the force from the hinge now also is making an effect. But we wanted to always pick whichever make our analysis easier. So a lot of times we pick relative to the hinge so that we can get rid of one of the torques and we don't have to worry about it. So let me show you a general method for balancing, solving this kind of static problems. First of all, we have to draw all the forces. We call the free body diagram, but now we have many, many forces, right? We call it an extended free body diagram. And then we also have on the label the distance, because when we do the torque, the distance matters. And then when you set up the torque equation, you need to pick an axis about which you wanted to calculate your torque, right? You're saying, okay, torque is a rotation relative to what point. You have to pick a point. Some of the good choices to pick such a point is where you can either allow you to calculate a force that you wanted to calculate, unknown forces, or eliminate a force that you don't want in the equation. So you can simplify the problem. Sometimes you really don't see it right away. If you don't see it right away, pick a point and then just try it out. If it turned out, if you need to realize, oh, actually I need to pick another point that's easier, and you can always do that. After you pick a point, you can write down your torque equation. You can also write down your force equation, and all of them have to be balanced. Okay. You need to solve all the unknown quantities, and you need equal number of equations as your unknowns. So sometimes it's a good way. Sometimes you need one equation and you're done, right? Sometimes you realize, oh, I have two unknowns and now I have only one equation. Knowing that, you know where to stop. You need, okay, I need one more equation, or I need two more equations, and that tells you where you would want to stop. All right, so let's take a look at another question about static equilibrium. Here we have a very light board, so that tells you don't have to worry about the gravity of this board. And the board is balanced, supported by two ends, here and here. So we know that there are forces applied at these balancing points. And then you have a mass M placed 2/3 of the way on the beam. Now, what is the ratio of FR over FL? So FR is a force, normal force provided by the one end of the beam pointing upward. The other force is a force provided by the pivot on the left end. How do these forces compare? What is the ratio between them? Right, so there's a hint. Now, before you, let's say pretend we don't have any hint. And we realize, okay, well, if we were to solve this equation, we know that we have to balance all the forces and all the torque. I don't really know which one to start first. So maybe it doesn't matter. If I list all the equations, eventually it's going to solve anything I want. I don't know where to start. So I'm going to start with one of them first. I'm going to start with the force, and you realize, oh, okay, all the forces upward has to add up to balance the force that is downward. So this is the equation. Okay, you realize, okay, that doesn't really tell me the ratio between these two forces, right? Okay, so which means I really needed the torque equation. So even if you can see, even if I did start with the one that is not very useful, that's okay. I can always go to the torque equation later. So here they give us a hint that let's consider the torque around the mass M. Okay, so let's consider the rotation around which point. Here, I want to show that depending on what the problem is asking you, you can pick your rotational point to make the problem easier. Okay, so here, let's pick it right where mg is. And that's going to tell you FR over FL, the ratio between these two forces. All right, I don't think that required too much of a discussion, so I'm going to go ahead and let you vote. If you need a moment to, feel free to take a moment to think before you vote, or you use your scratch paper to write it down, the torque equation, okay? All right, we will go for 10 more seconds. All right, any last minute votes? All right, let me go ahead and this. We'll take a look at this together. This is our results. We're quite all over the place, our answer choices. Okay, so you can see that there are different ratios that was given. Again, remember we said if you have a problem, then you try to solve it. It's always more helpful if you think of this qualitatively. Just think about which force has to be bigger. That either you might be able to eliminate some of the choices right away, or you can use that to double check your actual calculation, right? So in this case, if you pick the pivot point relative to mg, you see that these two forces are trying to make this to rotate relative to mg, and mg does not give you any torque. So these two forces are, one of them are trying to make it rotate counterclockwise, the other force trying to make it rotate the other way clockwise, right? So they have to generate equal number of torque in order for it to be balanced. So just by looking at the diagram, which force has to be bigger in order for it to be balanced, in order for the torque to be balanced? The force on the right has to be bigger, or the force on the left has to be bigger?
Force on the left, so it doesn't like tip over.
Okay, so the force on the left has to be larger or smaller? The force on the left has a longer level arm. What do you think?
Can I answer?
Of course.
So since on the left side the R is bigger, would the force be smaller on that side to balance out?
Yes. So if you think of this as sort of like a seesaw relative to this point, if one is a much longer distance, then this one has to be a smaller force. So FL has to be smaller than FR. So if FR is larger, then the ratio of FR over FL has to be larger than 1, right? So if you look at these answer choices, only one of them saying it's larger than 1. It has to be actually twice the F of the left, because you can see their level arm is exactly, this one has double the length than the other. So one of them has to be twice as much. So if you set up the torque equation about where mg is, okay, so FL give you a clockwise rotation, so that's going to be F times R. R is 3/3 of L. Oh, sorry, 2/3 of L. Then the torque from the right hand side is counterclockwise positive. So FR times L over 3, and that's positive. You can see you cancel the L, you cancel the 1/3, you get FR is 2FL, right? So which means FR over FL, the ratio is 2. So D is correct. Now, I know that sometimes this is counterintuitive, maybe not very intuitive to pick the pivot point right where the mass M is. Because you know this is not the real life. You think, okay, I'm not really rotating relative to that point, right? You might feel more natural to pick a point here or pick a point here. But as I said, those points are totally up to you where you want to pick. And you want to pick it so that the calculation can be easier. So for this problem, you don't have to pick it where the M. If you feel, I just don't want to pick with that point, you can put it here. Then that will give you a torque equation that calculates what FL relative to mg is. And then you can combine this with the force equation to calculate the FL, the other force. Eventually, they all will give you the same result. Okay, but if there are ways to simplify the problem, you would like to do that. So, okay, let's move on to look at a different balancing problem. Again, we have two little sharp supports. It's trying to balance a beam. Okay, so we have a 10-meter long board, 20 kilograms, and it has two supports, 1 meter from the board's center of the mass. So the board center of the mass is right in the middle, and these are put at 1 meter. Each of them is put at 1 meter away. So this is 1 meter, and this is also 1 meter. And right at the right, on top of the support on the right-hand side, you put a 1 kilogram block on it. And you also have a person, the mass of the person is walking out from that support. How far could you go? How far this person could go without the board tilting over? You want it to be in static equilibrium. Okay. So to solve these kind of problems, first, you wanted to be able to draw all the forces. We will call it to be an extended free body diagram because we wanted to label everything, all the forces, including the distance. So here, let's label all the forces. First of all, we have the gravity of the board itself, right? So that's acting from the center of the mass of the board, which is in the middle. So here you will put M board G. That's the gravity. And you have another 1 kilogram mass. So this one gives you a gravity pointing downward. Sorry, that is unnecessarily too long. Oh, my drawing is not updated. Give me 1 second. Let me update my share. Just 1 sec. This is another gravity, that's M of the weight G, mg. Okay, so not supposed to be that long. Let me make it a little shorter. This is another weight, right? From the 1 kilogram mass. And then you have the gravity of the person, which is pushing down as well, right? So there you have, this one is the largest actually. M of the person G. So I labeled all my gravities. Then there must be normal force coming from the supporting triangle. One of the normal force is here. N1, capital N or little n, doesn't matter. And one of the normal force coming from here. Okay, so a lot of times it might be also easier if you try to simplify it on a separate diagram without the picture sitting in the way. You can translate your diagram over and also by adding the distance between them. And also we're trying to figure out how far this person can walk without the board tipping over. So the distance between the 1 kilogram and the person is, we're going to call it distance x. And we're going to try to find out what x is. Okay. So now this is our free body diagram, and we labeled all the forces and all the distances. And now we're going to apply the force equation and the torque equation. But we'll just start with the force equation because at this point, it's not obvious to me which equation is easier, or maybe I do need both. So when you're not sure, simply just start with the force equation or the torque, doesn't matter. So let's start with the force equation. All the forces pointing upward have to cancel all the forces pointing downward. The force equation is straightforward to list, right? All the normal force, 2 normal force minus the 3 gravity downward has to add up to be 0. And now we need to apply the torque equation. We need to pick an axis where it rotates. And the choice of that point is totally up to you. It can be anywhere. anywhere. But we want to pick a point where maybe it's easier to calculate. So let's say we put it where the first support is. We're looking at the pivot point where right according to this point. Because that allows me to eliminate N1 in terms of my torque equation. So I think, well, maybe that's easier because that's one less force I have to worry about, right? And I don't really know what N1 is, so that's perfect. I don't have to calculate a force that I don't know. All right, then we have to add up all the torque. We just have to keep the signs plus or minus is correct. So the force, the torque that is going to relative to the first beam, and two, the normal force is trying to make the beam to rotate counterclockwise. So that gives you a positive torque. So that's positive N2 times 2 meters because this distance is 2 meters. Okay, the level arm is 2 meters. All the gravity is trying to, relative to our pivot point, is trying to make the thing rotate clockwise. So all the torque from the gravity are negative. So you put 1 meter for the level arm of the first gravity. The second gravity is at 2 meters level arm away. And the third gravity, the person relative to our red dot, is 2 plus x distance away. So x plus 2 is the level arm for my person's weight. Okay. So at this point, you can evaluate. As I said earlier, you can see whether you have everything you need or do you need to continue find more equations to solve. We have 2 equations we just listed, like 1 and 2. And how many unknown quantities? We have normal force 1, normal force 2, and the person's distance x. So we have more unknowns than we have our equations, which means we need more equations, we need more information. But then you might wonder, well, where do we get more information? Didn't we add up all the forces and all the torque, right? That's everything we know. There are anything from the problem setup that we didn't realize. So the problem is asking, what makes this X so special? This make the X special is we want to see the furthest distance you can walk without the board tilting over. So it's talking about a critical point, just like when we do the roller coaster problems, we were asking, what is the slowest speed that you can to make it over that loop? So at the top point where you have the critical point, here's the same. You don't want the board to tilt over. So when it's right at this point, you can see that the more the person walked toward that side, you can see just when it's about to tilt over and before it tilts, there is the beam is losing contact with your first support. Okay, that is when the furthest distance the person could walk. So at that point, your normal force at point 1 is 0. So that's a hidden information, a critical point that we can get from the problem. That's normal force is 1. So if we do know the normal force is 1, then we have got rid of one of the unknowns. We have 2 equations, 2 unknowns, and the rest is the algebra. We can solve for the distance the person could travel without the board tilting over is 0.2 meters away from the second pivot point. Okay. So that's it. That's one example showing in a more complicated problem where you don't really know where to go directly, you can start just by listing all the forces equal to 0 and all the torque equal to 0 and evaluate your unknowns and your number of equations, and eventually you can solve the problem. All right, so on Monday, we will continue to do another problem. Actually 2 problems on Monday we will do for static equilibrium. And after that, if we have some extra time, we will talk about universal gravitation, universal gravity on Monday. All right, so that's all I have for today. I wish you a great weekend and I'll see you guys next week. Bye everyone.
Bye, Professor. Thank you. Have a good weekend.
Bye. Thank you. You too.
Bye, Professor. Take care.
Bye bye. You too.
Oh, Professor.
Yes.
Actually, I had a question. I saw that in the in our schedule. It's the week.
Sorry, I couldn't hear you.
I'm looking at the schedule, and
Yeah.
so the final it would be in the first week of December. So I just wanted to know if it will still be on the Wednesday of that week.
Oh,
Because
I need to check the university's final schedule, and I
oh,
should
okay.
announce it to everyone. Yeah, you can check it too, but I just need to check. It's not the first week of December. We still have our class, right? So it's the week from, let me see, December 6th to December 10th is our finals week.
Right. Okay, right.
Okay. All right. Bye-bye.
Bye-bye.